Thanks everyone for showing up to these Zoom talks, and we're happy today to have Chelsea Walton of Illinois, and Rice and MSRI, one of our co-organizers for this great semester.
Yeah.
And she's going to be telling us about algebras in group theoretical fusion categories. And there's a bunch of links in the chat for some handouts and notes if you want to see them.
Yeah, including the talk notes. So this is kind of a mixture of a colloquium, algebra seminar, and technical talk. So it's going to go too fast for some folks, too slow for other folks. And I'm just trying to hit all the parts. So feel free to skip around the notes as you see fit. So this is joint work with Yibi Morales, who might be here, I don't know. Monica's here, Julia Plavnuk, Anna Rose Camacho, who's here, and Angela Tiberi. This is our Winner 2 group project. So thank y'all for coming. The link to the paper is in the chat. So I just pre-wrote these notes and I'm just gonna scan through. Let me know if I go too fast. I'm gonna keep it to 50 minutes, hopefully. So the goal is that we want to construct Morita Equivalents class representatives of indecomposable and semi-simple algebras and group theoretical fusion categories. Now, I'm going to explain all those words, but that's the main goal. You have some nice category, you can form module categories over it, and you can pick algebras to represent them, and you want these algebras to be nice. All right, so I'm going to spend most of the talk talking about why care about this goal. Secondly, how we achieve the goal. And thirdly, perhaps what we can do next. Feel free to ask some questions. Please interrupt. I guess if you chat, Noah will give me the questions. I can't see it. I don't know how to click on it when I'm sharing the screen. And I might stop to ask you questions because talking like this gets a little boring. So I might call some of you out, sorry. Okay, so let's get started. Why care about Morita equivalents? Well, the basic notion of Morita equivalents starts with rings. It's basically replacing ring theory with representation theory. So all of you know this, I think. You take two rings and we say that they're Morita equivalent if there exists an equivalence of categories of modules over them. It's a very, very useful notion. There are lots of equivalent notions of Morita equivalence, mostly due to Morita in the late 1950s. Here are a few of them. Well, I can talk about right modules, categories of right modules being equivalent, or I could talk about categories of left modules being equivalent. These are equivalent definitions. You have that two rings are Morita equivalent if and only if one ring is isomorphic to some idempotent times a matrix ring over the first ring times idempotent again. Full means that the matrix ring times idempotent times the matrix ring is equal to the matrix ring. All right, so that's another way of realizing Morita equivalence. Another way is having that the endomorphism ring of some progenerator of your module category, so some finitely generated projective generator, is isomorphic to S. So depending on the type of problem you're working with, you might, like this is used a lot in finite dimensional algebras. This is used, well, a fair bit in ring theory and category theory, but this notion of Morita equivalence is what we're really going to use in category theory, because we can really talk about modules and bimodules in a nice way. So what do you need? You need an SR bimodule and you need an RS bimodule so that when you tensor them together in either order, we get this isomorphism. Okay, so that's Morita equivalence. There are loads of nice ring theoretic properties that are preserved under Morita equivalence. So we call these Morita invariants. So if we have two rings that are Morita equivalent, we want properties that hold for R if and only if they hold for S. So examples of some of these properties are as follows. The Noetherian property is a Morita invariant. The semi-hereditary property is semi-prime, primitive, and so on. So for instance, if you have a commutative ring, it's prime if it's a domain. This semi-prime is a non-commutative generalization of a ring being reduced. So these are very, very nice ring theoretic properties that serve as Morita invariants. Now, the main example of a Morita equivalence is you have that a ring is Morita equivalent to any matrix ring over R. So, so if you have a theory where you don't care whether or not your matrix ring is replaced with the base ring or not, maybe Morita theory is the way to go. Okay, any questions on this? Yeah, no? Okay, let's keep going. Hear noise.
I said I'm good.
Oh, okay. Whoever said that.
That was me, Chris.
Oh, hey, Chris, how you doing?
Doing great.
Okay, why care about Morita equivalence? I mean, this is algebraically already nice, but it appears in a lot of fields, any fields, particularly in analysis and geometry. Now, I'm not going to welcome questions about this. I'm not an analyst, but I just want to give you a flavor of how it appears. So in analysis, there is a really nice theorem due to Brown, Green, and Reifel in the late 70s. It says that two C-star algebras that are either separable or unital or so-called strongly Morita equivalent, meaning that there's a nice bimodule that connects the two. So this is pretty analogous to this notion of Morita equivalence here, except you need some analytic properties on top of it. So two C-star algebras are strongly Morita equivalent in this sense, if and only if you have that the two rings are so-called stably equivalent. So what that means is that when you take the rings and you tensor them each by some algebra of complex operators on a separable Hilbert space, you get that these are isomorphic. So this notion of Morita equivalence is equivalent to this, okay, in functional analysis. Another way Morita equivalence pops up is due to a theorem of Joux in Poisson geometry. So this was developed in the late 1990s. Says, okay, let's take a regular Poisson manifold, and we want to know when is it so-called Morita equivalent to a Poisson manifold with zero bracket. So they cooked up a way of connecting the two again with a bimodule. Let's call it bimodule. Really, it's a symplectic manifold where you have complete Poisson morphisms from X to P and X to the, I guess, anti-Poisson manifold on Q, satisfying certain conditions. So this holds if and only if all the symplectic leaves of P are connected and simply connected and the fundamental class vanishes. So basically what this notion of Morita equivalence does is it gives you an equivalence relation on the collection of all integrable Poisson manifolds. That's the main key here. That's the main key. So again, we use this bimodule definition in these two settings. But we're here to talk about Morita equivalence in algebra, and that really pops up in its connection to physics. So I'll pause for questions before we move on. Okay, let's keep going. So Morita equivalence really shows up in the intersection between algebra and physics, particularly in rational conformal field theory. So rational conformal field theory is this nice blend of classic field theory, special relativity, quantum mechanics. Conformal comes in because you want all your transformations to be angle preserving, And rational comes in because all your dimensions in play are rational numbers. So some really important algebraic structures were developed to understand rational conformal field theories, namely these gadgets called modular tensor categories. So we've heard about these maybe in 12 talks, maybe in 20 talks throughout the semester. But if you don't know what they are, there's a link in the chat that gives a chart. You can start with a monoidal category, a category that comes equipped with a tensor product, a unit, associativity, and unit morphisms. This sort of mimics the definition of a monoid. You can build on an extra structure to get a so-called modular tensor category. So in particular, you want dual objects, you want a way of swapping objects across one another. That's supposed to be an isomorphism. And you want each object to be a direct sum of objects that can't decompose anymore. An example of a modular tensor category is category representations of a vertex operator algebra. Okay, so how do we get into Morita theory to study rational conformal field theories? Okay, so we need a notion of an algebra and a monoidal category. What is it? So usually, okay, when I teach grad algebra, I mean, probably most of us use Dumbin and Foote or maybe Artin. And what do? They take a ring and they build on it the structure of a vector space. This is sort of the opposite. You start with a vector space and you give it the structure of a ring. But we can work more generally. So you can take an object, say a vector space, if you like. You can pretend that C is vec. And you want a multiplication morphism and a unit morphism satisfying associativity and unit constraints. I'm always assuming that my algebras are associative and unital. So with this, you can talk about modules over algebras. So that's going to be a pair of an object equipped with an action map. I'm dealing with right A modules, satisfying associativity and unit constraints. And I'm going to denote the collection of A modules like so. Okay. And then we say that two algebras, let's say A and B, are Morita equivalent if and only if these two categories are equivalent as so-called C module categories. So I don't want to define what a C module category is, but that's why I put E.J. No's book in case you want to look up these definitions. But it mimics the definition of a module in the expected way, where C plays a role of a ring. All right, any questions on these definitions? All right, so what does this have to do with rational conformal field theories? Well, in rational conformal field theory, I mean, Anna will be able to speak more to this than me, but one is interested in so-called boundary conditions. And what this boils down to is studying very nice algebras in modular tensor categories, up to Morita equivalents. And so some papers that you want to look at that discusses this well and develops this theory are papers due to Runkle, Fuchs, and Schweigert. So in particular, if we take, let's say, representation category of a VOA, the types of algebras that we're interested in are semi-simple, which I'll define, symmetric Frobenius algebras, and these algebras yield a boundary condition. And if we were to fix a boundary condition and look at all the algebras arising from it, they're all Morita equivalent. So studying boundary conditions of rational conformal field theories boils down to studying nice algebras in this category of representations up to Morita equivalents. Okay, any questions about this page? Let me know if I'm going too fast. I'm just whipping through it. Okay, I got thumbs up. All right, let's keep going. So Morita theory, it's very nice. I mean, so what is Morita theory? We're understanding categories of modules, but it's even nicer if you have an algebra that represents categories of modules, especially if the algebra is really explicit, especially if the algebra has a formula that you can compute with. But determining this is, that could be a little tough, It's also convenient to have an explicit algebra that has, well, that's nice in a couple of ways. So it's convenient to have nice Morita equivalence class representatives of algebras in monoidal categories that, boom, boom, stop. My pug, that are nice property-wise and structure-wise. Here's one way that an algebra can be nice property-wise. So it's really convenient to have an algebra that is so-called decomposable. What that means by definition is that its corresponding category of modules is indecomposable as a module category. Just like for rings. I mean, you give an algebra a name if its corresponding category has that same feature. So that goes with semi-simplicity. An algebra is semi-simple in a monoidal category if and only if its category of representations is semi-simple. So these are nice algebras in a property sense. Structure-wise, it's really convenient to have even more structure on an algebra, namely, your representative is Frobenius. The Frobenius algebras are quite beautiful, Okay, so what happens? Well, given an algebra, it has a Frobenius structure if and only if there exists two morphisms, co-multiplication and a co-unit, so that the object, co-multiplication, co-unit, forms a co-associative, co-unital, co-algebra, all right? And whenever you have two structures and you put them together, you need some compatibility between the two. So you need a compatibility condition between the multiplication and the co-multiplication. And that's satisfied by this diagram here. So if I take an algebra, I multiply and co-multiply, I want that to be the same as going along this path or along this path. Here are my associativity morphisms. Sometimes they're omitted in books. Sometimes you just have a square here, and a square here. But I actually need to throw them in because in the categories that we're going to deal with in a few minutes, the associativity morphisms are not necessarily the identity. They matter in the data. Okay, so that's a very nice structure that we could have on Morita equivalence class representatives. Even nicer when the multiplication, when I first take the co-multiplication, then apply multiplication, I get the identity map on A. And when I apply the unit and then the co-unit, I get some scalar multiple of the identity map on the unit. So such a Frobenius algebra is called special. Depending on where you look, the definition might change, but this is the notion of special that we're using here.
Chelsea, can I ask a question?
Yeah.
So can I see the Nakayama automorphism here somewhere, or?
Yeah, I can write it down, but we don't need it for paper.
In the presentation you're giving here, does it appear, or is it kind of just not appear here?
No, not appear here. Yeah, but I can write down the the version of it.
Okay,
yeah.
But it's not. Good. Thanks.
Yeah, it's not here though. It's in a paper. I think I found it first in a paper Runkle. And Stigner. Stigner. But you need to throw in associativities. They're always working in the strict case. Always, because they like diagrams.
Okay. All right. Thank you.
All right. So recall the goal is to construct Morita equivalence class representatives of indecomposable, semi-simple algebras in these nice monoidal categories, which I'll define in a minute. And when we do that, we're also going to get that they happen to be Frobenius as well. Yeah. So before we move on, are there any other questions on this page? Okay, I need to tell you now about these group theoretical fusion categories. What are they? Why care? Blah, blah, blah. All right, group theoretical fusion category, of course, it's going to have something to do with group theory, but they're really, really nice. They are fusion categories. So they're monoidal categories that are semi-simple, K-linear. Again, you can find definition of fusion category on that chart. Have a lot of nice features. And they depend on group theoretic data. What do they depend on? 4 bits of data. First of all, you take a finite group. You take a 3 co-cycle on it, or class. You take a subgroup of your finite group G, and you take a 2 co-chain beta on your subgroup so that its differential is equal to omega. All right, so those are your 4 bits of data. Now, what is the definition? It's a category of bimodules. It's a category of bimodules. Okay, so first of all, we take this category vec G omega. So that was discussed in Victor's talks in the intro workshop. Very, very important category. There's already a lot that you could do with that. So this is a category of G-graded, finite dimensional K vector spaces. The simple objects of the category are just one-dimensional vector spaces. So K, the ground field K, concentrated in degree G, some element G and G. And this omega comes in because the associativity constraint changes a bit. It's not just the identity map. You use the 3 co-cycle to give you a different associativity constraint. And the fact that this satisfies the Pentagon axiom is equivalent to this being NH3. Okay, so that's a nice monoidal category. And you can take algebras in it. So let's form the twisted group algebra on K with respect to the cocycle B. So we can take these simple objects here, let G run through the subgroup K, and then twist the multiplication by this beta. Now this is going to be an associative multiplication because we required that the differential in beta is equal to omega. Yeah, so that could be checked. Okie dokie. So once we have a monoidal category and we have an algebra in it, we can form a category of bimodules. Now that is going to be monoidal by taking the tensor product to be that over the, let's call it the base algebra, involving K and beta. The monoidal unit of the category is going to be the base algebra. And this associativity and unit constraints are going to be induced from the monoidal category, vec G omega. So these group theoretical fusion categories, they're really nice because if you have like a conjecture or something like this about fusion categories, these are kind of the first place you go to test it out because it's a very concrete category. Here's some examples. So let me put this here. So if we take K to be E, and as a result, beta will be just a trivial 2 co-cycle. Maybe I'll just make it so that you can see everything, okay? Then we recover vec G omega. And of course, if we were to turn off omega, then we get vec G here. So these are nice categories, and it's a special case of your group theoretical fusion category. We also pick up rep G by turning off omega and letting K be the whole group G with trivial co-cycle. So we get RepG as a group theoretical fusion category. And we also pick up bi-smash products as well as bi-cross products as well, representation categories of these. So these are all really nice examples of group theoretical fusion categories. We get representation categories of groups, duals of groups, quasi-Hopf algebras, as well as semi-simple Hopf algebras. Here, I see chat. Is there a question?
No, that was just me reposting your links.
Oh, okay. I swear I see the orange alert and I'm like, oh.
Sorry about that.
Oh, no problem. But yeah, are there any questions about this? Group theoretical fusion categories are really cool. I think they're cool. So we're going to play this, we're going to achieve the goal for these. Okay. That all was part one. What's the goal? What's the context? Why should we care? Definitions. Now let's get into how the goal is achieved. Cooking up nice Morita Equivalents class representatives of algebras in these categories, or in these categories. Okay, there's a very, very important special case. Well, I shouldn't call it a special case. It is a cool theorem. And it's one of the papers that I linked in the chat, a paper due to Victor. This goal was achieved for vec omega. It goes like this. Every Morita equivalence class of indecomposable, semi-simple algebras in vec omega is represented by one of these twisted group algebras. And I'm going to label it with the L and psi, because these are going to vary through your Morita equivalence classes. That has to be different than the K beta, which is going to define your group theoretical fusion category. So the goal is achieved for vec omega, which I think is really, really cool, represented by these twisted group algebras. So what we want to do is build on this theorem. We want to upgrade this to a category of bimodules over vec omega. So I guess we could have done it directly with that explicit bimodule category, but instead we shot for something more general. So our first theorem is working in a more general setting. We just work with a category of bimodules, in general. And then the application will be for this setting group theoretical fusion categories. So let's take a monoidal category. Let's call it V, because eventually V is going to be vec omega. And let's take A, our base algebra, to be a special Frobenius algebra. What we do is we construct a very explicit monoidal functor, or we give the free functor the structure of not only a monoidal functor, but a Frobenius monoidal functor. So a monoidal functor is a triple. It's a functor equipped with a natural transformation and another morphism. And essentially what it does is it sends algebras to algebras. And a Frobenius monoidal functor is a 5-tuple that eventually what it does is it sends Frobenius algebras to Frobenius algebras. So if you look at our paper, we have lots of commutative diagrams. I don't know, maybe we have like 20 pages of commutative diagrams. It's crazy. And Anna and Monica, y'all did a great job because, very complicated. Most of that is proving this result. We have a very explicit formula for this Frobenius monoidal structure, and we show that it satisfies all the axioms that we need. Okay. So what we want to do is apply this result to send algebras in vec omega to algebras in group theoretical fusion categories. First step, we need the base algebra, namely our twisted group algebra, to be a special Frobenius algebra. And we have that. That's a proposition in our paper. Now we can apply it to obtain a nice Frobenius monoidal functor going from vec omega to a group theoretical fusion category. So that's step one. You can at least send algebras here to algebras here. At least gets us started. Any questions?
This is Victor Lustig. So, do you understand right? This Frobenius monoidal functor is similar to Lex monoidal functor, so something like that. So it's not quite monoidal.
Oh yeah.
Functor.
So in this paper, we don't assume strong. So by monoidal we mean lax.
Okay,
Strong is too strong.
So it's something like it's lax monoidal and off lax monoidal, and there's some Frobenius like compatibility between them. Is that kind of the
Yeah. Great. We're too lax to say lax. Yeah, always lax. We just want algebras to go to algebras. That's it. Frobenius to go to Frobenius algebras.
But it's probably, is it also, in particular, it's also op-lax. It sends co-algebras to co-algebras.
Yep. Because it sends Frobenius algebras to Frobenius algebras. Yeah, that's the notion of Frobenius monoidal functors due to Day and Pastro. And I got this idea because my student Harshit, you were digging into this stuff, and I thought, oh, that is nice. I'm going to use that. He shows me nice papers. So anyway, listen to your students. All right. Okay, let's keep going. Okay, so now that we have a Frobenius monoidal functor, that's on the free functor, namely sends an object X to this object in your group theoretical fusion category. And we have this result of Victor that a collection of twisted group algebras represent Morita equivalence classes in vector omega. One would think, well, let's just consider the image under this functor and hope that it represents Morita equivalence classes of algebras over here. So let's just give that algebra a name. We call it a twisted Hecke algebra because the simple objects of the group theoretical fusion category parameterized by double cosets and a representation. Yeah. So anyway, we call it a twisted Hecke algebra, and the multiplication is twisted by cocycles. So it happened to work. Okay, so this is our first, well, no, that was our first main theorem. This is our main theorem. First part is that every Morita equivalence class of indecomposable, semi-simple algebras in a group theoretical fusion category is represented by one of these twisted Hecke algebras. So we have the complete analog of Victor's result. Next part of the theorem makes the connection really tight. We have that two of these twisted Hecke algebras are Morita equivalent. Let's say twisted Hecke algebra depending on the pair subgroup L of G and two cochain psi on L, so L and psi. This is Morita equivalent to the algebra depending on some L prime psi prime, if and only if the corresponding group algebras are Morita equivalent as algebras in vector omega. Now, what's really nice to make this uber concrete is that there's the result of Natali that says precisely when these algebras are Morita equivalent. Namely, you want the two groups L and L prime to be conjugate by some element of G, and you want a certain two cocycle that's a little too complicated to write down, but it depends on both psi and psi prime to be trivial as two cochains in L prime. Okay, any questions on this?
So I have another question. So if I understand correctly, your group theoretical category is in the same kind of Morita class as vector omega. Is that right? Like they have the same Dirichlet double, or Grunfeld center?
Oh, there's two notions of Morita equivalents. Okay, yeah. So there's like Morita equivalents of algebras in a category. So that's sort of like internal to the category. And you could talk about external Morita equivalents, like categories.
Bimodal,
Yeah.
like omega and
Yeah, that's different. Yeah, that's different, but related in a way. So I'm talking about internal Morita equivalents.
Yeah, but is it the case that your categories are Morita equivalent to vector omega in the sense that I was saying?
Yep.
And then you can transfer module categories abstractly from vector omega to the other one, but you're giving like a concrete realization of this.
Yes,
kind of
exactly. That's where all the intuition came from. So like we had this idea, we knew it was right, but to actually write it down explicitly.
Right.
Yeah.
Okay.
Yeah.
Great. Thank you.
Yeah, thank you for pointing that out. Yes.
And do your results about translating algebras hold at that level of generality? If I have, say, I have C and D and they're higher Morita equivalent, and I have a complete description of all the algebras in C, can you always just write down for me some Frobenius functor built out of that Morita equivalence, such that the algebras here are exactly the images of the algebras there, or is it special to vec omega?
Well, we have this. Oh, maybe I'm going to get to that. We have this result, and we have a result that's on this level that will address your question on page 9. So maybe that'll answer your question.
Great, thanks.
We have a slight generalization. Well, actually, no, it's not slight. You'll see. Okay, page 9. Page 9. Okay, so here's some examples before we get there. Let's take vec G without the omega. So we could talk about a group theoretical fusion category with the base being Kg. All right, now this category of bimodules is equivalent to rep G. So I could send Morita equivalence class that's no omega here. I could send Morita equivalence class representatives of algebras in vec G to Morita equivalence class representatives of algebras in rep G. You gotta have to do this in 2 steps. First of all, you use our formula to send algebras here to algebras in this bimodule category. But then there's a paper of Natali, 2002, that gives you explicit monoidal functors between these 2 categories. So you have to use that as well to get in rep G. But it can be done. Working more generally, you can take Morita equivalence class representatives of algebras in vec G and send them to representation algebras and representation categories of bi-smash products as well. Okay, so this proof, the proof of this result. Again, we wanted to work more generally because, I mean, the algebra that we're dealing with is just some image of Frobenius monoidal functor on going from a category to a category of bimodules. So that's a really general setup. We want to, I guess, go along this track to prove this result. So this is what we do. Okay, so first of all, we want a way of taking a pair of Morita equivalent algebras, let's say in your source monoidal category, and sending it to a pair of Morita equivalent algebras in, let's say, your target monoidal category. And we cook up conditions so that that happens. So take 2 monoidal categories, S and T, along with some monoidal functor. We want algebras to go to algebras, call it gamma from S to T, so that it preserves epimorphisms and so that the natural transformation of this monoidal functor is epi for all objects S and S prime in script S. Under this condition, if we have that, if S and S prime are Morita equivalent algebras in this category, we could push those over and get Morita equivalent algebras in T. In this case, let's call the functor Morita preserving. This is Morita equivalent algebras in S to Morita equivalent algebras in T. So that's really useful because that at least gives us one direction of our theorem. Okay, and another part, applying this to categories of bimodules. Now let's take our monoidal functor V and take a category of bimodules over V with respect to the base being special for Frobenius. So this isn't quite working in the greatest generality that Noah's talking about, but it is starting with a category and sending it to a category of bimodules. We get that two algebras are Morita equivalent in V if and only if their images are Morita equivalent in the category of bimodules. And this is the functor phi that we use, the functor phi, not just any old functor, but the functor phi that we constructed. So one direction was not so bad. The forward direction, we had to show that our functor phi was Morita preserving. It satisfied these hypotheses. The other direction, the backwards direction, that took some work. I think, that took some work. We had to construct other Morita preserving functors to go from the bimodule category back. Yeah, that took some work, but it's done. It's done. So then we apply this to V being vector omega, A being the group theoretical fusion category with respect to the group K and cocycle beta to get our main result, this one here. Okay. Any questions before I wrap this up? Okay, well, let's wrap it up. What now? What now? Morita equivalence, it's ubiquitous, appears everywhere. People really care about it. And it's really nice when you have representatives in Morita equivalence classes that are nice, nice algebras. There are physical uses of Morita equivalence, particularly involving algebras and modular tensor categories. And we achieve the goal for algebras in group theoretical fusion categories, which are, again, nice monoidal categories. So naturally, one question could be study the intersection. So for this, we would need the group to be, needed to be abelian to start off with, abelian to get braided, along with some other conditions. So maybe the intersection could yield some results here. Be kind of nice. Also, another, I guess, leg of this work is that we develop lots of tools to determine when two algebras are Morita equivalent in general, not just for vector omega or for group theoretical fusion categories. I mean, we work a lot with general monoidal categories. So maybe there's some nice new applications of these tools. In any case, I am very interested in your thoughts on any of the above, and thank you for listening. That's it. Under 50 minutes.